Okay, we want to look at the Gram-Schmidt process, Gram-Schmidt orthonormalization. This Gram-Schmidt process will give us an orthonormal basis for a vector space if we have any basis at all. So let's just start with a simple example that really gets the main idea of the Gram-Schmidt process. Okay, so let's say we have basis one, 4, 5, 3. And this is a basis of R2. Sorry, it's allergy season. Can't do much about this, but the coughing. But okay, so here's a basis of R2. And it's easy to see that this is a basis. We can do the dot product of these two vectors, and it's clearly not 0. So this basis is not orthogonal. Okay, it's not normal. Neither of these vectors has magnitude of 1. The dot product is not equal to the product of the magnitudes, which you can easily verify, so that these vectors are not parallel, but you can see that very easily if you just look at slopes. Okay, let's go ahead and illustrate these vectors. 1, 4 might have a direction about like this, and 5, 3, maybe a direction like so. So let's just say that this is 1, 4, and this is, actually, let's go ahead and put these into the column vector notation. Okay. So here we have the vector 1, 4. Here we have the vector 5, 3. Now, we have this operation called vector projection. Okay. So let's just call this vector V1. Call this vector V2. Vector projection, we project V1 onto V2. Now the projection is a simple enough operation if we look at it geometrically, but we have to see how to calculate this thing. Okay, we project this vector at a right angle, and the vector that we get here is the projection of that vector. So this vector is the projection onto V2 of the vector V1. Now we can use dot product and by extension an inner product to project one vector on the other. Okay, the advantage or the point being that if we look at this right triangle, okay, this vector here has a magnitude that's equal to, if this angle's theta, excuse me again, this vector is V1, and it has then a magnitude V1, so that's magnitude V1 is going to represent the length of this vector, or the magnitude of this vector. This vector has magnitude equal to the magnitude of V1 cosine theta, and the direction of V2. Well, this means so the projection onto V2 of the vector V1 equals magnitude of V1 cosine theta, which gives you the magnitude of the vector multiplied by V2 over the magnitude of V2. Now, why V2 over the magnitude of V2? And looks like I need to aim this camera a little better. Yeah, it's going to mess up the other one. Let's do this so we get the whole board. And I think we're still good with the other camera. Okay, so why this vector? Well, we know that this vector is a unit vector in the direction of V2. Okay. So all we're doing then is multiplying the magnitude of V1 of the projection, sorry. I'll just do that a little sloppily. Magnitude of projection times a unit vector in the direction of the projection. Because again, what we want is the vector here in the direction of V2, whose magnitude is this leg of this triangle. It's the right triangle. If the angle is theta, then the magnitude of this has to be magnitude of V1 times cosine of theta, just by straightforward right angle trigonometry. Okay, so there we have the logic of it. And you want to understand the logic of this thing, which is quite simple, so that you don't have to rely on a formula you might forget. And whether you remember the formula or not, if you don't understand the formula, you don't understand what you're doing, and you're not going to retain it as well. You're not going to have the tool as available to you. Okay, so for many reasons, we want to understand this. Then we can say that the projection onto V2 of the vector V1 equals magnitude of V1 cosine theta times, and I'll put parentheses there just for a little clarification. We don't really need them. Multiplied by V2 over the magnitude of V2. Now you can condense that into a formula that makes it less obvious what this means. You know, you just say that's maybe this, and you can do that, but why obscure the meaning? Well, formula's more compact, whatever. Now I'm thinking that I'm missing something because there's a formula I recall, and I'm used to the formula. It has a magnitude of V2 squared in the denominator. So I want to check my memory here, make sure that I'm really doing this correctly. And as an honest, something doesn't feel right, but there's a very straightforward derivation here. So let me check out my derivation. Okay, you have this unit vector. That is a unit vector in the direction of V2. We can enhance the picture slightly. Just saying, okay, here we got V1. Here we've got V2. Here we've got the projection of V1 on V2, and that's where I'm wrong. Oh, never mind. Nothing wrong with what I've got. I've just got one more step to do here. Okay, but anyhow, to enhance this, and then we've got V2 over magnitude of V2. Now, magnitude of this vector is about 6, at 5.8, something like that. So about 1/6 the length of that vector. So here is this red vector is V2 over the magnitude of V2. Okay, well, I've left one step off because, of course, we don't know cosine theta, do we? Okay, so what are we going to do about this magnitude of V1 cosine theta? Do we have to go out and calculate cosine theta? Well, that's easy enough to do. We just take the inverse cosine of the dot product divided by the product of the magnitudes of the two vectors. Well, we don't want to do that, so we want to observe something. Okay, let's go back to the definition of dot product, which I'll write over here just to remind us. V1 times magnitude of V1 times magnitude of V2 times the cosine of theta. Notice that right here in this expression, we have our magnitude of V1 cosine theta sitting there staring us in the face. And I still don't have the camera far enough over there, so let's just do this. Okay, so there we have it. And this tells us that, the thing that we need here, the V1, magnitude of V1 cosine theta, can be calculated easily enough. Just by dividing both sides by this magnitude of V2. I talk a lot about formulas and not using formulas when you can use geometric reasoning or some other kind of reasoning. It makes it easier to remember the formulas. And if you think you're always going to be looking up the formula, better to remember, better to understand where they come from. Again, gives you a much better, deeper understanding of the topic, which you can then apply more efficiently when you have a situation where you need it. On the other hand, remember there's a magnitude of V2 squared in the denominator of this formula, which kind of reminded me that it wasn't done yet, okay? So you got magnitude V1 cosine theta here. You use the definition of the dot product, and you see that magnitude of V1 cosine theta is just this dot product divided by the magnitude of V2. So now I can write, I'm going to rewrite this formula. As a matter of fact, what I'm going to do is I'm going to just do a little erasure here. And I'm going to say that this magnitude of V1 cosine theta, which is now here, we got from here, gives us V1 dot V2 over magnitude of V2, because that is what we get here, times V2 divided by the magnitude of V2. Okay, so this is my preferred way of writing this thing. It shows you clearly that you've got a unit vector here that's multiplied by the projection, magnitude of the projection. Okay, magnitude of projection times unit vector, which is what you're really doing. Every textbook I ever see lumps these two magnitude of V2 expressions into a single denominator with a square on it. Now, this is the formula that you would use if you're doing this mindlessly. This is the formula you use if you want to remind yourself of what's going on. Okay, I like this a lot better than this, although the connection is very clear. Now, if you understand what's going on well enough to look at this and see, well, yeah, this V2 could go under here, there's your unit vector and so forth. If you want to think that much, or if you naturally can think that much, then that's fine. If you have that insight and you're going to maintain that insight, then this formula is just fine. If you're not sure you're going to maintain that insight, I like this better because it connects this, and I like the idea of thinking through what you mean when you construct the projection. Okay. Now I've got a decent video camera here because apparently my bandwidth causes Zoom to fuzz out sometimes. So I found that I've wasted a lot of time doing videos that people can't read because Zoom, and it's not, I don't think it's Zoom's fault. I think it's my provider. They're not giving me the service I pay for. Okay. There we have it. Okay, well, now, again, our topic here is Gram-Schmidt orthonormalization process. So I'm going to go to Gram-Schmidt now. Knowing now that we can project one vector on another, I better capitalize that S. Okay, Gram-Schmidt. There's more to Gram-Schmidt orthonormalization process. Okay, one thing we can do. Again, we've got these vectors now. Vector V1, vector V2. If we can calculate the projection, which we can easily do, and I'll calculate it for our vectors in a minute, but that's just calculation, okay? There's a process to be understood. So here's your projection. onto V2 of the vector V1. And it's a vector. So we put an arrow over the projection, and actually we've got two vectors here, and we put arrows over them. And it's easy to forget. If you don't have an arrow over this projection, it's the scalar projection, which is just the length of this, and positive or negative, depending on whether this angle is acute or obtuse. Okay. In any case, once we have this projection, then notice that this vector here is orthogonal to V2. Okay. Now, what's that vector? Well, let's just draw a vector diagram here, a little bigger maybe, so we can label it in case that becomes something we actually want to do. So we got this vector, and we've got this projection, and we've got a right angle. So this vector is V1. This vector is the projection, and it means all this. I'm not going to write out all those symbols, but when I write the final thing, I'll have those symbols. And this vector is orthogonal to V2. So we'll call this V1 perpendicular. That's not a standard notation, but for the purposes here, that means V1 component perpendicular to V2. We can calculate the projection. So we can calculate V1 perpendicular. Why? Because this vector plus this vector equals this vector, equals V1. The projection plus this V1 perpendicular equals V1. So we can write projection, which is shorthand for projection on V2 of V1. And let's go ahead and write it out now. On V2 of V1, plus the vector I designate as V1 perpendicular, I denote as V1 perpendicular, equals V1. Well, if that's the case, how do we calculate V1 perpendicular? We know V1. We can easily calculate the projection of V2 on V1. Let's just do some algebra. Let's subtract this from both sides so that V1 perpendicular equals V1 minus this projection. That's it. So now we have two perpendicular vectors. Okay. So I'm going to say the set V1 perpendicular V2 is a basis of R2 We know it's a basis because there are two vectors in a two-dimensional space, and they're certainly not linearly dependent, because that means in R2 they'd be multiples of each other. And this is perpendicular to this. Okay. And we're assuming they're non-zero. They have to be non-zero because remember, V1, V2 was originally a basis. Since V1 and V2 formed a basis, we know that those vectors aren't parallel. Okay, so it's now a basis of R2. Not only that, this is an orthogonal basis, which you know from your study of basis makes things particularly simple. Okay, so it's a basis, it's an orthogonal basis, and often we want an orthonormal basis. Okay, well, if we want an orthonormal basis, we just go ahead and divide both these vectors by their magnitudes, and it's orthonormal. Orthonormal means orthogonal and unit vectors. So we have a basis of orthogonal unit vectors. So we say that's an orthonormal basis. The Zoom recording, some of this might be obscured, might not by the watermark, but there we have it. Okay. Now there's one modification to the process I gave you for finding the orthonormal basis. We know we're looking for an orthonormal basis, even if we aren't. It really helps if we first normalize V2. So what we would want to do is, and I'm just going to picture it. This makes a calculation a little simpler. And you know we're going to have to normalize V2 anyhow, divide it by its magnitude, make it into a unit vector. So we got V1, that's V1. And V2. If we use V2, not V squared, this red chalk erases badly, so I have to use drastic measures here, which means I have a slightly damp board. Okay, this vector here is V2 over the magnitude of V2. Well, that simplifies calculation of the projection. So we can easily show that. And let's call that V2 norm. Okay, call that normalized V2. Now, you know, when you see it in your book, you're going to use different letters once you normalize things. I'm pretty sure that's where your text means it. Hadn't really looked at it. V2 normal is normalized. Okay, So now your projection onto V2 norm of V1 equals leave myself room, just V1 dot the normalized V2 multiplied by the normalized V2. Okay. You don't have to divide by a magnitude of V2 here or V2 norm here. You don't have to divide by a magnitude of V2 norm here because the magnitude of V2 norm is 1. So it simplifies the calculation if you first normalize V2. So that's the way we're going to approach it when we go to higher dimensions. If we had 3 vectors, V1, V2, V3, to form a basis for R3 or any 3-dimensional space with an inner product, if you've got an inner product, you can always do this, then you can just start with 2 of the vectors, okay? Normalize the second one, and then subtract the projection from the original vector to get the vector that's normal to V2. And if you first normalize that, calculation's simpler. You're going to have to normalize it anyway, you might as well. Okay, well, then you go to V3. Now, what are you going to do with V3? Well, you're going to subtract the projection of V3 onto V1 and onto V2 and so forth. Okay, we're going to do that, but let's just do a quick example. And the example that we started with. Okay, so okay, V1, V2 is 1, 4, 5, 3. So I'm going to say V2 norm, and I'm going to call that U2. Okay, V2 norm just equals the vector. Now I'm going to put it in column form. 5 over the square root of 34. 3 over the square root of 34, because the magnitude of this 5 squared is 25, 3 squared is 9. Add them up, you get 34. And the magnitudes and then the square root, Pythagorean theorem that I'm not even going to justify anymore. There it is, okay? Then projection of V1, projection onto, and I'm not going to call it V2 norm, I'm going to call it U2 now. The projection onto U2 of V1 equals V1 dot U2 over magnitude of U2 multiplied by U2 over magnitude of U2. Remember, U2 is normalized, so its magnitude is 1. That's just V1 dot U2 multiplied by U2. Projecting V1 onto U2 is particularly simple if U2 is already a unit vector. Okay, there's a projection. Now we're going to let U1 be what we would have formerly called V1 perpendicular. It's V1 minus the projection of V1 onto U2, which is, write it down here, V1 minus V1 dot U2, U2. And now we can just take our coordinates and calculate it. Okay, so it's, go back to columns. 1, 4 minus 1, 4 well, we've done the notation. And the reason I'm using columns is so I can put this into standard matrix form. So let's do the dot product the way intended. It's going to be minus 1, 4 multiplied by 5 over the square root of 34. Three over the square root of 34. Times the 5 over square root of 34, 3 over the square root of 34. And that's not written very clearly, but we understand this vector is the same as this, it's just a U2. And now we can do the arithmetic. You get 5 over the square root of 34 and 12 over the square root of 34, which is 17 over the square root of 34 times 5 and 3 over the square root of 34. And it's just simple calculation from now on. Notice that you have square roots of 34 here, so that square root isn't going to bother you. You don't ever really need to calculate it because you're always going to be multiplying it by itself. So we're going to have 17 times 5, which is 85, over 34. And 17 times 3 is 51, that's over 34. And not only that, it gets a little better. 85 over 34 comes down to 5 halves or 5 halves. And 51 over 34 is just 3 halves. And often you get that sort of handy simplification, especially in early steps. 5 halves, not 3 halves. Jumping the gun. Try to erase this as neatly as possible because Zoom also not Zoom, but Zoom combined with my internet provider. Tends to blur erasures very badly. And could have been a better 3. Let's see if we can repair that. Okay. So that's what? That's -3/2. And that's 4 minus 3/2, which is 8/2 minus 3/2. So that's going to be 5/2. Okay. That's going to be our U1 vector. And now we have an orthonormal basis, I hope. Let's see. So U1, U2 equals -3/2, 5/2. And actually, I'm one step shy of orthonormal. And then we have 5 over the square root of 34, 3 over the square root of 34. Now that's clearly orthogonal. Okay, just in case you can't see it, but clearly orthogonal because the dot product here is obviously 0. You get -15, and then it's over 2 times the square root of 34, and plus 15 divided by 2 times the square root of 34 gives you 0. This is orthogonal. It's not orthonormal. Okay. To get it orthonormal, you're going to have to normalize this vector. So it's orthogonal, almost orthonormal. So one more step to orthonormalize it. Well, that's the basis for just what you have with 2 vectors. Let's consider now what you have, or what you have to do if you've got 3 vectors, say, that form a basis. So that would be, for example, 3 vectors in R3. And we'll formalize the process just a little more. Yeah, just looking at my board situation. Okay, now the rest is actually pretty simple. There's just one step that you might be a little confused about. Because we've gone into 3 dimensions and you visualize it, you've got to be able to visualize R3. Get that on here. So again, we're going to go into R3. Let your basis in R3 now be one, 2, 3, 3, 2, 1. Zero, 2, 0. Now, just to be sure that this forms a basis, let's just do the dot products. The dot product of this and this is not 0, then these 2 are not orthogonal. Dot product of this and this is non-zero, then these 2 aren't orthogonal. If this dot product is not 0, these 2 aren't orthogonal. Well, it's very simple. All these dot products are positive. None of them are 0. So you can calculate it yourself. But now, we'll let this be a basis of R3. R3 we know has dimension 3. We've got 3 vectors here. None of them are orthogonal to one another, but to any of the others. It follows we have a basis. Okay, so here's our basis. And I should have said, and I'm just going to kind of notate it. This will be V1, V2, V3. Here's how we go. You know, we're going to start with U3. So we're going to start with V3 and project it onto V1. So we're going to let actually I'm going to do U2. I'm going to start with U1. Okay, let U1 equal V1 divided by the magnitude of V1. And calculation straightforward. Square this, you get 9. Square this, you get 4, which makes 13. This makes 14. So there's our vector U1. I'm going to actually use a third letter here. I'm not sure your text does this. Okay, I'm labeling these U1 and U2. I'm going to double these. I'm going to make them W's. Well, I'm going to make this one W. This is still going to be U, but I messed it up. So I'll erase it. I'll get rid of that. Let's write it out correctly. Okay. Let W1 equal this. We're going to let U2 equal U1 minus the projection onto I'm just having all kinds of trouble here. V2. Minus the projection onto W1 of V2. Okay. You know, this is going to, the projection isn't going to be 0 because W1 is just parallel to V1, which is not perpendicular to V2. So the W1 is not perpendicular to V2. So the projection is not going to be 0. Okay, so U2 is going to be V2 minus this projection. This is going to give you a vector perpendicular. Orthogonal to W1. we're going to let W2 equal U2 divided by U2. The next step, I'm tempted to do in 2 steps, although you can do it in 1. Yeah, I'm just going to do it in 1. Maybe explain. Okay, now let U3 equal V3 minus the projection into W1 of V3. And this is going to subtract off the part of V3 that's parallel to W1, meaning the part that's parallel to V1, actually. Okay, so we subtract that off. Now that doesn't guarantee that this vector is also perpendicular to V2. So to make sure that happens, we can subtract off its projection onto W2 of the same vector, because we're trying to take away the parts of V3 that are parallel to V1 and parallel to V2. Okay, how do we take off the parts that are parallel to these vectors? Well, if you think back to what we did originally, this projection is the part of V1 that's parallel to V2. And we, for reasons I hope you understand by now, subtract that off, leaving only the part that's perpendicular, okay? Well, we take off the part that's parallel, part of V3 that's parallel to W1, and the part of V3 that's parallel to W2. And we have it, okay? We have what's left, which has to be perpendicular to both W1 and W2. So U3 is perpendicular to W1 since we subtracted off the part that's parallel to W1. And U3 is perpendicular, did I say parallel before? It's perpendicular to W2 as we subtracted off the part of V3 that's parallel to V2. So there we have it, except now we want to normalize U3. So we're going to let W3 equal U3 divided by the magnitude of U3. Well, that's it. Okay, W1, W2, W3 are now all unit vectors, and each is orthogonal to the other. This is an orthonormal basis. If you were in W4, well, you'd have a V4, wouldn't you? And as long as your V4 along with V1, V2, V3 make a basis, and of course, if you're in 4 dimensions, then the vectors of length 4. But if all those conditions hold, you're going to do the same thing with W4 or with V4. You're going to have already done this. You're going to already have your W1, W2, and W3. And then your U4 will be your V4, but then you got to subtract the projection onto W1 and the projection onto W2, and then the projection onto W3. So you'd have 3 of these projections to subtract. Nothing mysterious about that. That's what works. That can be proven with symbols. I'm not going to go through the proof. I'd like to, but this introductory level course, if you understand the process and hopefully the reasons behind the process, then you're doing okay. Now, we see from this example that we can extend this to any dimension. Yeah, might get tedious, but it's easy to program it. So, and then you wonder, well, why should I have to do this? If we can program it, why not just do it? Well, you have to understand it. If you don't know what the program's doing, you don't know what's going on, and you can't visualize it, you can't use it. Okay. You know, all we do is train you to use this, use this, use this, and use this. We might as well just write a program that uses this, uses this, uses this, uses this, then we don't need you. Okay. Well, we need the flexibility of your mind. And this is why we teach you to think. Okay. And think through these things and understand more deeply than any computer, at least so far, can do. Okay. Now we could actually do this calculation, but it gets a bit tedious, and your text is going to have examples of these calculations. So there's nothing new to do by just running through this sequence of calculations. It's not going to be as obvious as it is in 2 dimensions. So there's really no point in doing that, so I'm not going to. Here's the process. You just you start by normalizing your first vector. Then you take your second vector and you subtract its component in the direction of the first, and then make that into a unit vector. It gives you your W1. That's all that's going on here. For V3, you subtract its component in the direction of now what we call W1, the normalized V1. And also its projection on W2, which is the normalized part of V2 that's orthogonal to V1. Okay, so you subtract off both of those projections. And if you got a V4, well, you subtract its projection onto W1, and then subtract its projection onto W2, and its projection onto W3, which are the normalized vectors that you get from these processes. And you normalize that, just divide it by its magnitude. Yeah. We're not going to make you do that for a 10-dimensional vector. Probably won't even make you do it for 4 dimensions. If you understand it in 3 and understand what's going on, then you're in good shape. Okay. In general, with Gram-Schmidt, we've replaced dot product with inner product because we know, for example, in function spaces, an inner product can be defined by an integral. It's not a dot product. And the idea of perpendicularity becomes orthogonality. Orthogonality being defined by the condition that the inner product is 0. So we don't literally have the 2- and 3-dimensional picture anymore. But everything that we do with Gram-Schmidt can be done. So if we have given basis V1 through Vm, Okay, let W1 equal V1 over the magnitude of V1. Now, I just tried to take a look at your book because I don't pay that much attention to notation. I think the notation your text uses for general inner product is pointy braces with the two vectors, okay? Down here it would be square root of this inner product. So there's your W1, then W2, well, U2 equals V2 minus the projection of V2 onto V1, which because V1 onto W1, since W1 is a unit vector, that projection is just V2 W1 inner product times W1. And then let W2 equal U2 over, I keep wanting to write magnitude, and I could, because the magnitude is defined to be the square root of the inner product of U2 with itself, but I'm going to write it out explicitly. Then U3 equals V3 minus V2 W1 times W1 minus and it's V3, not V2. And remember, these projections simplify due to the fact that W1 and W2 are both unit vectors. So now W3 equals U3 over the square root of the inner product of U3 with itself. Maybe a little hard to read, but there it is. And then U4 would equal V4 minus the inner product of V4 with W1 times W1 minus the inner product of V4 with W2 times W2 minus the inner product of V4 with W3 times W3, and I'm not going to write it out, the W4 would then be U4 divided by the magnitude of U4. And that's it. Okay, so we generalize this to any inner product. It doesn't have to be a dot product. It doesn't have to be a Euclidean space. Any vector space. We've got a basis. We can convert it to an orthonormal basis. Okay, One other thing, we're doing WebAssign here, and WebAssign sort of drives me nuts. I'm using the standard WebAssign assignment, which I think is a little bit too trivial. But if that's the conventional wisdom, since this is the first time I've done WebAssign for this course, I'm going to go with it. But it drives me a little bit nuts when you have multiple opportunities on a problem and you have two choices. Okay. So I will be asking from now on in this course that you submit your written work on any assignment. Okay. In the same way you submitted written work on other assignments. That isn't necessarily an official assignment until I write it out, but believe me, I'm going to do that soon. Okay. I want to see your written work. I want to see your reasoning. If you have a true or false, I hate true or false questions, and you have so many of them in WebAssign. They don't make you think through anything. You just guess, and then, it didn't work, I'll guess this. Yeah. And I can't eliminate guesses because on some problems you need a couple of opportunities, okay? You need to be able to revise a small error. So I'm not happy with that aspect of WebAssign. Anyway, I want to see the written work, okay? You get credit for your homework, but if you don't learn anything, you don't pass the test. I want to see it so I can help you prepare what you need to do in order to pass the test. Okay, so please get in the habit of doing that from now on. Okay, thank you. Good luck.